Right, we'll continue from where we stopped in the previous lesson. In fact, we were discussing at last the equilibrium constant. Equilibrium constant in terms of the concentration, and equilibrium constant in terms of concentration was explained. And equilibrium constant in terms of concentration, we wrote the Kc statements. Can you hear me clearly? There's a complaint from some of the students. The voice is not clear. Right, we were discussing about the Kc calculations. Before that, I explained about the equilibrium constant, how to derive the Kc, and then the factors which affects the equilibrium was discussed. And then I said there are two equilibrium constants. Equilibrium constant in terms of concentration and pressure. In the previous lesson, I derived the equilibrium constant in terms of concentration, which is Kc. That is the product of the concentration of the products over the product of the concentration of the reactants, each raised to their stoichiometric coefficients. And we wrote the Kc expressions for various homogeneous as well as heterogeneous equilibrium. And then afterwards, we derived the units for these. I said the units of these equilibrium constant Kc depends on the stoichiometric coefficient. Sometimes the Kc may not have units. Sometimes the Kc will have different units based on the stoichiometric coefficient. Now the question is, when you have different physical states, remember always you should include one physical state. The Kc expression should be homogeneous always. The Kc expression should be always homogeneous. You should never use different physical states in the Kc expression when you're writing the Kc expression. That's number one. And number two is always use square brackets, because square brackets have specific meaning. It is the concentration in moles per decimeter cube. That is exactly what square bracket means. And then the third, if you have water as a solvent, right? Water as a solvent, we never include water. Now, what is meant by water as a solvent is that, for example, in this case, in this particular example, water is not a solvent. Here, water is not a solvent. Water is a reactant. How do you know that? Can you see water? It has broken down into H+, and the OH- has reacted with the dichromate, right? So water is a reactant here, right? But we don't include water in the Kc statement, not because it is a solvent. No, it's a reactant here. We don't include the water in the Kc because it's in a different physical state. You can notice water is in liquid, others all aqueous. That's the reason why we don't include water here. But if water is a solvent, usually we don't include, like for example where water is a solvent, say ethanoic acid reacting with water. It doesn't react with water, it dissociates into ethanoate ion and H3O+ ion. That means water takes H+ from the acid and forms the hydrozonium ion. So what happens here is the ethanoate ion gives H+ to water. So water just takes the H+. It doesn't react with H+. So H+ in aqueous media is available as H3O+. Right? So in this case, water is just a solvent. It's not a reactant. It's not going to react and form a different compound like it did in this example. Right? So in this situation, we don't include water in your writing the Kc. So here you have, even though everything is in liquid state, for example, if everything is in liquid state, water is not included because water is a reactant, not a reactant. It's a solvent in this case. I hope that point is clear. I think there was a question at the beginning of today's lesson. The question was, if water is a solvent, would it be always in aqueous state? So if it's the water in solvent, when you're writing the equation, you can just omit the water and write this as aqueous, right? You can just simply omit the water and say aqueous. Aqueous. Then you have ethanoate ion and H+ ions. Or if you're including water, that's okay, but you do not include the water in the Kc expression, right? Water in aqueous state and liquid state? No. Actually, water is liquid. There's no aqueous state for water. because anything dissolved in water is what we call aqueous. Anything dissolved in water is aqueous. There's no aqueous state for water. So when you say ethanoic acid plus aqueous gives ethanoate ion and H+, what is meant here is ethanoic acid is aqueous ethanoic acid, meaning ethanoic acid is in water. It's not that the water is in aqueous state. There's no meaning of water being aqueous. Water is liquid. Right? Anything dissolved in water is solution, aqueous. Is that point clear? Okay, good. Let me explain to you the difference between aqueous and liquid. So water itself is a liquid. Anything in pure state, if that means you heat and melt it, that's liquid state. Aqueous means anything dissolved in water, right? So for water, you can't put aqueous for water. There's no aqueous water. Water is always liquid. Water is always liquid. There's no aqueous water. But if you dissolve any substance, for example, HCl in water, we call that HCl as aqueous. So if you come across any aqueous state, that means that particular substance is dissolved in water. That is the meaning of aqueous state. Is that clear? Is that point clear? Aqueous and liquid difference? So there is no aqueous water. There's only liquid water. My explanation is not completed, but I just wanted to make sure that you know the difference between the aqueous and liquid. Got it? Okay. Next, now, whenever water is a solvent, especially this happens when you have, say, acid or alkali. So, for example, you have ammonium hydroxide in water. It will break down into ammonium ions and hydroxide ions. This is aqueous. Aqueous, water is liquid, and aqueous. Now, in this example, like the example which I wrote before, let me write that as well. This is aqueous, water is liquid. You have ethanoate ion. Can you hear me now? I'm sorry, there's a power cut, so I had to log out. Can you hear me now? Extremely sorry about that. Okay, so I was explaining about the difference between aqueous and liquid. Now look at these examples again. Now here, acid is aqueous, water is liquid, ethanoate and H+ is aqueous, and this is also alkali is aqueous, water is liquid. Now, water is aqueous. You can't put aqueous for water, right? Now, these both examples are examples where water is acting as a solvent, not a reactant. Why? Because you can see nothing happens to water. Ammonium hydroxide gives hydroxide ions, breaks into NH4 plus and hydroxide ions in the presence of water. It's just dishing the presence of it, react with the water. Another good example is that salt. We take sodium hydroxide or sodium chloride salt, put to water, what happens? Will it react? No. When I put this to water, I put water here. It breaks into Na plus ions, aqueous, Cl plus ions, aqueous. This is the easiest example to understand this concept. Now here, what is not a reactant? Sodium chloride salt will not react with water. For salt react with water, what will be the product then? It dissociates into ions in water. It just breaks into the cation and the anion. That's all. So this is a good example of water being a solvent, not a reactant. Right? Likewise, in these two examples, water is a solvent, is not a reactant. Right? Just like a salt dissociate into ions, is ammonium hydroxide and ethanoic acid just dissociate into ions. That's all. So now, whenever you have NaCl in water, now instead of writing water here, I can replace the water with aqueous. It doesn't mean water is aqueous. Water is liquid. But I can put instead of water AQ to show that NaCl is in aqueous state. In other words, NaCl is in water. So likewise, I can replace this liquid water as AQ. AQ doesn't mean water is aqueous. Water is liquid. But I can replace instead of water AQ, because if I write the water here, I can't balance this equation, right? I balance is this equation balanced? No, it's not balanced. Where is it in the product side? You can't balance the equation. Therefore, we put AQ. Likewise, these equations, you can't balance this. If you're balancing, I'll put hydrazonium ion, H3O plus here. So therefore, these three examples, water is acting as a solvent. It's not a reactant. Therefore, in that situation, we can remove the water and put AQ, aqueous. That means this acid or the alkali or the salt is in water. That's the meaning of AQ. It doesn't mean that water is AQ. Right? I don't know if that's clear. If it's not clear, let me know. I'll explain again in a different way, a different example. Right? So that's the difference between. So anyway, in these situations, we do not include water for two reasons. One reason is that here the water is in different physical state. Can you see? Water is a liquid, right? Others are aqueous. Water is a liquid. So that's why we don't include water. The second reason is water doesn't react here. It's just a solvent. Like when you put NaCl to water, just NaCl breaks down to Na plus and Cl minus. There's no water here as a product. It just dissociates into ions in aqueous media. That means water is acting as a solvent. Right? It's just a solvent. So likewise, water here, I can just substitute this water or this water from here, and instead of water I can write AQ. AQ means this acid is in aqueous state, meaning dissolved in water. Alkali is in aqueous state. Sodium hydroxide is in aqueous state. Then the equation is balanced. Don't worry about extra H and O. I hope that point is clear now. Right? So let's see the calculations involving this KC. I'll start with the question 4. These steps had to be followed in the calculation. It says X moles of sulfur dioxide is mixed with Y moles of oxygen. At equilibrium, it is found that Z moles of oxygen had reacted. That means I'm mixing initial moles. Sulfur dioxide is X. Oxygen is Y. Initially, there's no sulfur dioxide, right? And out of X, it says at equilibrium, it was found that Z moles of oxygen has reacted. So you have X moles of sulfur dioxide, Y moles of oxygen, mixed together, but at the point of equilibrium, out of Y, only Z has reacted. Not the entire Y is not reacted, only part of the Y is reacted, Z. Write the expression for the equilibrium constant Kc and provide that the total volume is V dm cube. Now the reacting stoichiometric is 2:1 here, right? That means 1 mole of oxygen needs 2 moles of sulfur dioxide. If 1 mole of oxygen reacts, it reacts with 2 moles of sulfur dioxide. Therefore, if Z moles of oxygen reacts, it reacts with 2Z moles of sulfur dioxide. Why 2Z? Because reacting ratio is 2:1. You are mixing X and Y, but out of X is not reacting, only 2Z is reacting. Out of Y, only Z is reacting, right? So look at the stoichiometry. The 2 moles of sulfur dioxide reacts with 1 mole of oxygen to give 2 moles of sulfur trioxide. Likewise, 2Z moles of sulfur dioxide reacts with Z moles of oxygen to give 2Z moles of sulfur trioxide. 2:2. 2:2, right? Let's find the number of moles at equilibrium. Moles at equilibrium. Initially, you have X. Finally, you have 2Z. So X minus 2Z is a moles remaining at equilibrium. Why the moles at equilibrium is needed here? Because we are going to write the Kc statement. And I explained last week, the Kc is written at the point of equilibrium. Kc is the concentration of the products over the reactants at the point of equilibrium, right? So this is Y minus Z, the number of moles at equilibrium. This is 2Z. So once you find the moles, now you can work out the concentration. Concentration is the moles over volume. Moles over volume. Right? And now you can write the case. Right? Concentration of sulfur trioxide to the power 2 over concentration of sulfur dioxide to the power 2 times the concentration of oxygen. What you do is you substitute these concentration terms, and you know how to derive the units. It will be per mole dm cube. You can derive the units at the end. So you can substitute these values. This is 2Z over V squared, and X minus 2Z over V squared, and Y minus Z over V. And we can simplify this further. I can simplify this further. Let me write it here. I can cancel the V's, right? I can cancel this V squared. So I have 4Z squared, X minus 2Z squared, Y minus Z, and this V at the denominator can be brought to the numerator, and the units here will be per mole dm cube. That will be the units, right? Okay, so these steps have to be followed. Always you need to know the initial moles, right? Reacted moles, because initial moles will know the reacted moles, because some of the reactants may be in excess, so only part of the moles react. Then you have to work out the moles at equilibrium, because moles at equilibrium will indicate that will be helpful to find the concentration at the point of equilibrium. So once you find the concentration at the point of equilibrium, you can substitute the values of the Kc statement and derive the value and the unit for the Kc. So these 4 steps have to be followed when writing the Kc.